Hello, my name is Roy Simpson. I'm an instructor of mathematics at Cosumnes River College in Sacramento, California. This is a first in a series of lectures on quadratic equations and how to solve quadratic equations and how to solve quadratic models and build quadratic models. This is essentially your first foray into a really detailed exploration into parabolas and quadratics, things that are not linear in mathematics. And in the first attempt here, we're going to go ahead and define what a quadratic equation is, and then from there we'll talk about what a quadratic equation, maybe the different forms it takes, and how to solve those different forms. Now, the official definition of a quadratic equation is an equation of the form ax squared plus bx plus c is equal to 0, where a is non-zero. If a is going to be 0, the reason why we say a cannot be 0 is that if it is, then it's just bx plus c is equal to 0, and that's actually a linear equation. So you'll see the difference between a linear equation and a quadratic is this power of 2 placed on the exponent of your variable. That's essentially how you're going to tell that you have a quadratic equation, is when you have an equation, first of all, and that the power on your lead term is 2. And then there's all these different types and forms of quadratic equations, and maybe I should show you a few of them here. Something like if you have ax squared plus bx is equal to c, that's also a quadratic equation. Ax squared is equal to c, that's a quadratic equation. Even this stuff, a times the quantity of x plus, let's say h being squared plus c is equal to 0. The reason why I say this last one is quadratic, even though it's not explicitly given in the original definition of a quadratic equation, is that if you were to multiply out this polynomial, or this binomial, I'm sorry, you would get the following. So that's just a times x plus h times x plus h, and then plus c. By the way, the only variable in all of these equations is x. Okay. And anyhow, if you distribute through that binomial there, you'll have a times x squared plus 2hx plus h squared plus c. And then when you distribute the a through the parentheses, you'll get ax squared plus 2ahx plus ah squared plus c is equal to 0. And in reality, this is just saying, listen, I have a coefficient on x squared. I have some number coefficient, or 2ah, on the x term. I'll just go ahead and for now call that b. And then I have some set of constants. Remember, a, h, and c are all constants here. So really, that's just some number. And I can call that c prime or anything I want. But you see in the end, after I multiply this, this equation out and clean it up, distribute through parentheses and whatnot, it really does turn it right back into a quadratic equation of the form ax squared plus bx plus c is equal to 0. So all these are just different forms of a quadratic equation. The one we're going to actually concentrate on here is a very special form. It's quadratic equations of this form that I've highlighted, a times the quantity x plus h being squared plus c is equal to 0. The reason why I like this form initially is that they're very easy to solve. If somebody gives you an equation like this, they're actually not too bad. Now, before we can actually go into solving them, I have to state one theorem, just a single theorem, and then we'll be able to solve pretty much everything in this lecture. The theorem is called the extraction of roots theorem. And this is something that will help for many applications in the future. So this is one of those things that you shouldn't gloss over. You should spend some time really thinking about it. The statement is, if you have an equation of the form x squared is equal to k, where k is just some constant, some number, then it turns out that x is equal to plus or minus the square root of k. This is only true, by the way, in equations. All right, so I just need to say that first of all. And so a simple example, let me go ahead and write out a couple examples here actually to justify that this is true. If I told you that x squared is equal to 25, what could x actually be? Well, a lot of people think, well, I'll just take the square root of both sides. And if I take the square root of both sides, which is not a bad idea, if you take the square root of both sides, you'll get x, because a lot of people think that the square root of x being squared is just x. It's actually not, but let's just say for a moment that it is. And then everybody knows that the square root of 25 is just 5. But actually, there's another number I could have plugged in for x here. I could have plugged in x equals a negative 5. You'd have to agree that when I plug in negative 5 and square it, negative 5 times the negative 5 will also give me 25. So why is it that when we took the square root of both sides, why didn't the square root return both the positive and the negative 5? Well, a couple reasons. We did something wrong. A lot of people don't realize it, but you do something wrong when you take the square root of both sides if your equation has a square in it. Turns out, and maybe this is a sub-theorem, I'll just write it over, I'll just write it right here, theorem. Turns out that the square root of x squared does not always return x itself. It returns the absolute value of x. In other words, the square root of simple example, actually, let me just do it this way. For example, the square root of 5 being squared, well, 5 squared is 25, so that's the square root of 25, which is 5. Oh, look, so the square root of 5 squared is 5. But I thought you said that it wasn't always that way. Well, it's not. Because look, if it's the square root of negative 5 being squared, well, let's take care of the inside of that square root. So negative 5 times negative 5 is 25. But the square root of 25 is 5. So notice I have a negative 5 here that I'm about to square and then take the square root of. And it doesn't return a negative 5, it returns a positive 5. In both cases, it returned a positive 5, but the first case, I had 5 squared. The second case, I had negative 5 squared. This is just a justification that the square root of a number being squared is only going to return the positive number. So it has to rip off any negatives that might have been in that x. The squaring actually removes the negatives, to be honest with you. But that's kind of a background as to why this extraction of roots theorem is true. Essentially, the extraction of roots theorem is just saying anytime that somebody hands you something like x squared is equal to 49 or something like that, you know the answer is going to be plus or minus the square root of 49, or in other words, plus or minus 7. And you can check that. If you put a positive 7 and square it, it becomes 49. If you put a negative 7 in, it also becomes a 49 after you square it. So I suppose what I'm really trying to say here is that x could have been positive or negative. The squaring takes away the negativity of a number, so we would never have known. So when we try to solve an equation like this, you have to include the negative possibility as well. All right, so now that we know that theorem, x squared equals a number that x is equal to plus or minus the square root of that number, we can now actually solve a lot of quadratic equations. So the example set I'm just going to title solve each. And then in parentheses I have by extraction of roots, because it just depends. Someone might tell you, your instructor might tell you to solve using the extraction of roots theorem. Others just might just say solve. That's generally what I do. I tell my students solve. Using any method you know, solve these equations. And here's our first example. Now, for those who have not watched my entire lecture series, starting with a review of elementary algebra, how I solve something like this might be very foreign to you. But what I teach in my elementary algebra, my pre-algebra courses, and then therefore in my intermediate algebra courses, is a method for essentially solving any equation. Doesn't matter if it's an equation that's linear or quadratic or cubic or even trigonometric. Any equation that you face, as long as it has one version of a variable, I have a method for it. And the reason why I introduced this method is because students tend to get locked up in, I know how to solve a linear equation but not a quadratic, or I know how to solve a linear and a quadratic but not a rational, or they go down the list. They don't generalize very well. So here's a good generalization. Given an equation with one version of your variable, the first thing you're going to do is list out what has happened to that variable. The reason why I say this is because if somebody were just to give you this equation, they obviously are trying to hide the value of x from you. You don't know the value of x, you don't know the value of the unknown, so you have to do some work to unlock that value of the unknown. The way you unlock it is to think in terms of a puzzle. Somebody hid this value from you. They did a bunch of manipulations on your variable x here. They did a bunch of manipulations on it to hide the value from you. So you have to list out what they did. When you list that out, essentially you could think of it this way. It's like that's what somebody did to tie a knot around that variable so you can't open it up. So when you list out what's happened to the variable, then after that you can untie that knot. That means go list out how to undo everything that they did to hide the variable. You untie that knot in reverse order, by the way. This is best seen through examples. So we'll see it in this example very easily. And also what's nice about this method is that it introduces a very advanced idea in mathematics called the idea of an inverse. And that's super important, and this hopefully will make that idea a little bit easier once you get there. So I usually start these with a little question. What happened to x? What did they do to x? And first thing they did, let's see, here's x right here. The first thing a person did to hide the value of x from me is they squared it. Essentially, you're going to follow the order of operations. You look through this and you go, did they, if there are any parentheses, I look on the inside of the parentheses, that type of thing. And eventually you get down to, okay, here's the variable x. Did they do any exponents to it? Yes, they did. They squared it. So I'll write that down. It's the first thing they did. Now, after they squared it, following the order of operations, after you take care of exponents, what did they do? Well, the next thing they did is they multiplied it by 2, again following the order of operations. After they multiplied it by 2, they subtracted from that 7. So they squared it, they multiplied it by 2, and they subtracted from it 7. And remember, the order of operations says that if you have a fraction bar in your statement, in your expression, that a fraction bar is essentially a grouping symbol. It groups the numerator separately from the denominator. So we're essentially taking care of the numerator first. So x gets squared, it gets multiplied by 2, then it gets subtracted from by 7. After all that mess is done, so you have 2x squared minus 7, what's the next thing that they did to hide the value of x from you? They divided it, whatever that result is, they divided it by 3. That's all they did. They did all that and said, oh, by the way, that's going to be 4. So we need to untie that knot. In other words, unlock that variable. And when you untie a knot, you always start with the very last knot that was tied. So the last thing that they did was they divided by 3. So the first thing we're going to do is untie that division by 3. The opposite of division is multiplication. So in fact, I'm kind of cheating on the wording here. It's not really the opposite. Mathematically speaking, it's called the inverse. The inverse of division is multiplication. So instead of dividing by 3, we're going to multiply by 3. The next thing we're going to do, after we take care of untying that division, is we're going to untie this subtraction of 7. What's the inverse of subtraction? Addition. So we're going to add 7. Then I'm going to keep climbing that ladder there. So let's see the next earliest thing they did to tie up this variable is they multiplied it by 2. The inverse of multiplication is division, so we're going to divide by 2. And finally, the last step here is to note that basically to untie their first step, which is they squared. Well, the inverse of squaring something is taking the square root. So I have a road map here. This is what I'm going to do to both sides of the equation. Let's go ahead and start. So they had 2x squared minus 7 all being divided by 3 is equal to 4. From my road map, I already tell myself I'm going to need to multiply both sides by 3. I'll do this in red. So I'll grab this left-hand side and multiply it by 3. And I'll grab this right-hand side and multiply it by 3. When you do that, the 3's will cancel on the left-hand side. By design, it will always work that way. And you end up with this nice, beautiful 2x squared minus 7 is equal to 12. Now let's go ahead. I'm going to drag this up here. The next step, so this step is done. Next step, I tell myself I'm going to have to add 7 to both sides. So if I do that, if I add 7 to both sides, I'll get 2x squared is equal to 19. So I'm done with that. The next thing I tell myself I need to do is divide both sides by 2. So if I divide both sides by 2, I'll show that step. I didn't show the addition of 7, but 2 over 2, that's just 1. So I get this beautiful x squared is equal to 19 halves. Let me drag this up here because I'm running out of room. And now that I've finished that step, I have to take the square root of both sides. Well, either you can consider it taking the square root of both sides, or you can consider it using the theorem we just mentioned a moment ago, this extraction of roots theorem, where you have x squared is equal to a number, then x is equal to plus or minus the square root of the number. So using the extraction of roots theorem, or taking the square root of both sides, you'll get x is equal to normally the square root of 19 over 9. But because it started out with x squared, we don't know if that x was positive or negative in there. So we have to make a note. It could be plus or minus square root of 19 over 2. And that's it. That's your solution. Do not grab a calculator. So here's where I'm going to make a distinction for a lot of students in any kind of math class. A math class is not a calculator class. It shouldn't be. If your instructor allows you to use a calculator on something like this, and they tell you can use it always, you should tell them shame on them and tell them to contact me and I'll chew them out. That's really the idea behind learning mathematics, is to get as mathematically mature as possible before grabbing a calculator. So this is known as an exact answer. And trust me, this is actually much easier to leave like this than it is to punch into a calculator. If you wanted an approximate answer, you would grab a calculator. But exact answers are great. Let's just leave it like this. Now, before I move on to the next example, I want to note something here. Notice that the power on this equation was 2. And notice how many solutions we got. X equals plus square root of 19 over 2, and x equals a minus square root of 19 over 2. There's 2 solutions, and the power is 2. Notice way back when you're solving linear equations, the power is always 1 on x, and you only got 1 solution. So you might start thinking right now, wait, so I should get the same number of solutions as the power on my equation. And in general, that is true. There are exceptions, and we will see exceptions like this. But for the most part, you could say that the number of solutions to an equation is at most the power on your variable. That's for polynomials and stuff like that. Let's take a look at another style of equation here. This might not look like it's similar to the last one, but it's very similar to the last equation. In fact, it's a little bit easier. Remember, I told you that you could list out, what's happening to your variable if you have a single occurrence of that variable. But we actually have two occurrences of x squared. We have the one on the right-hand side and the one on the left-hand side. However, remember when you're solving any type of equation that involves variables, you want to get all your variable terms to one side. That's usually, in fact, that's almost always the very first thing you're going to do. So let's go ahead and move all of our variable terms to the left-hand side. So I'm going to subtract 0.7 x, I wrote a 0.9, 0.7 x squared from both sides. If you do that subtraction, you'll get 0.8 x squared on the left-hand side. On the right-hand side, the x squareds cancel, and you're just left with 26.2. Before you continue, if you look at a problem that has decimals in it and you don't want them in there, you're more than welcome to multiply both sides by 10. It's always a nice tactic because sometimes it's just horrible dealing with decimals. So there is a little bit of preparation before you tackle an equation and try to solve it. There's this idea of gathering all the variable terms to one side, this idea of getting rid of fractions or decimals. So that's really what I'm kind of trying to show. Let's go ahead and multiply both sides by 10. When you do that, you get 8x squared is equal to 262. And now you can start solving this. And I'm just going to list out, and some people might ho-hum about this. Why is he always listing this out? The reason why I'm listing out the steps of what's happening to x is because I'll have some students that immediately right now try to take the square root of both sides. And that is a very bad idea. So let's just ask what's happening to x. Okay, the first thing that happens to x, so whoever hid x in this equation, they squared it. Remember, follow the order of operations. After you do exponents, you take care of any multiplication there is. If there's multiplication, we'll list it out. There happens to be. It's being multiplied by 8. And there's really nothing else that's happening to x. So to untie to undo what they did, we'll start at the last thing they did, which is multiplied by 8, and we'll do the inverse operation, which is division. So we'll divide by 8, and then we'll undo their first step here. They squared, we'll take the square root. Let's go ahead and do that. So if I divide both sides by 8, on the left-hand side, the 8's cancel nicely. 8 over 8 is just 1. You get a 1x squared equals, and then 262 over 8. 8 doesn't go into 262 nicely, but we can reduce that fraction. So I'm going to go ahead and show the reduction here. They're both even, so they're both divisible by 2. 2 goes into 8 4 times. So basically all I'm doing is I'm factoring a 2 out of the 8 and the 262 and canceling them. 2 goes into 262 131 times. Well, at this point, I know that that cannot be reduced any further, so that's just 131 over 4. And now, let's see, after we've divided by 8 and reduced any fractions if we could, we'll go ahead and take the square root of both sides. So let's see, I take the square root of the left-hand side, it's just x. I take the square root of the right-hand side, and it's the square root of 131 over 4, except using the extraction of roots theorem, we have to write the plus or minus here. Or you could just think logically. You didn't know it in the beginning if x was positive or negative. And if it's negative, well, when you square it, the negative disappears. If it's positive, you square it and it still becomes positive. So you have to list out the fact that it could be positive or negative. Before I move away from this problem, I want to mention one more thing. If you're following my lecture series, I have not talked about reduction of radicals. However, you might have learned about how to reduce a radical or simplify a radical in a previous course. So if that is the case, you can go ahead and split this fraction actually this radical, into a fraction. So you have the square root of 131 divided by the square root of 4. And at this point, you know the square root of 4 is just 2. So that'll be plus or minus root 131 over 2. If you've never been taught that, and students in my course, while you have been taught that in a previous course, I don't hold you responsible for it until we hit radicals later on in the course. So you can answer with the square root of 131 over 4 right now. But it is nice, good form to actually simplify a radical if you can. So let's try another example here. This will be very similar to the last example in a way. Again, I like to do some preparation on an equation before I even begin to try solving it. The first thing I notice here is that this one has fractions in it, and I don't want to work on an equation involving fractions if I don't have to. So remember what I've been saying this entire lecture series. If you have an equation that starts with a fraction, you can get rid of that fraction by multiplying both sides of the equation by the LCD. I should mention, just to let you know, that this whole multiplying both sides by the LCD business, you can always do if you have only one variable in your equation. Like this has x's, so that's fine. But if I have an x and a y, likely it's not a good idea. But that's usually if you have an x and a y, you're not solving, you're trying to graph. That's completely different. All right, so I'm going to go ahead and multiply both sides by the LCD here. Let me switch pens. Multiply the left-hand side by 4 and the right-hand side by 4. I'll distribute that 4 into each of these parentheses, to each of the terms essentially. And let's see, 4 times 17 is 40 plus 28 is 68 minus, and then the 4 times x squared over 4, well, the 4's are going to cancel, so it's just minus x squared. On the right-hand side, distributing the 4 against the 43 gets me 160 plus another 12, that's 172, minus 4x squared. Now I have a choice. What side, now that I don't have fractions anymore, I can kind of start getting into the solving mode. What side do I want to gather my x squared terms on? I think for me, the left-hand side is a good idea because if I add 4x squared to both sides, I'll have positive coefficients on my x squareds. So let's see, 68 plus 3x squared is equal to a 172. And now I can start asking that question, what happened to x? Because see, I have one version of my variable now. At this point, this is the point where I can start asking what happened to x. And I'm not going to write it down as far as the question, but I'll just list it out. The first thing that happened to x, it gets squared. The second thing that happened to it got multiplied by 3. The third thing that happened to it, they added 68 to it. So my roadmap for solving this equation, I'm going to undo their addition of 68 first by subtracting 68. I'm going to undo their multiplication of 3 by dividing by 3. And then finally, I'm going to undo their squaring by taking the square root. Let's do it. Subtract 68 from both sides. Oops, incorrectly wrote that. When you subtract 68 from both sides, the left-hand side becomes 3x squared. The right-hand side, let's see, 72 minus 68 is 4, so that's 104. And now the next step is to divide both sides by 3. So let me go ahead and write that in. Divide this side by 3 and the other side by 3. I could already tell you this is not a good-looking fraction. 3 doesn't go into 104 nicely. Luckily, 3 cancels with this 3. 3 over 3 is just 1. So I get x squared is equal to 104 over 3. And finally, I'm going to take the square root of both sides. So that'll give me x is equal to the square root of 104 over 3. But don't forget the plus or minus, because you have no idea if that x in there was negative or positive, because the square will make it disappear no matter what. So you have to list out the fact that it could have been positive or negative. That's the answer. By the way, I might as well just show you, if you're asked to find the approximate, not the exact, but the approximate solution, you would, if you have a graphing calculator, hit the second button to access your second menu, and you see the square root button is right above your x squared button. So if you hit that, you get the square root, and you can just type in 104/3. End that parenthesis. So this is saying I'm taking the square root of everything in this parenthesis. Hit enter, and it's roughly 5.9. I'm rounding to the nearest tenth here. So let me go ahead, move this off the screen, and write in that that's roughly plus or minus 5.9. That's if you're asked to give an approximate answer. So in this example set, this is the final example here, and we have 3 times the quantity 8x minus 7 being squared is equal to 24. A lot of students are very tempted to multiply out 8x minus 7 times 8x minus 7. If you did that, you would end up with 2 versions of x. You'd have an x squared and an x, actually. And you would be complicating the equation. Anytime that you add more versions of your variable, you're overcomplicating an equation. The goal is to have as many versions of your variable in an equation as possible. So let's go ahead. There's no fractions, there's no decimals, there's nothing to really clean up initially. So let's just list out what's happening to our variable. The first thing I look at here, I'm jump inside the parentheses, just like I would with PEMDAS. Take care of any exponents inside the parentheses. There are none inside. So I go to multiplication. X is being multiplied by 8. After it gets multiplied by 8 inside the parentheses, it gets subtracted from by 7. And that will get me done with the inside of those parentheses. So now I take a look at 8x minus 7. What's happening to that? Oh, it's being squared. And then after it gets squared, so now I have 8x minus 7 squared, what happens? Well, it gets multiplied by 3. So to undo all of this, I will start untying this knot by doing these things in the opposite order. In other words, the last thing they did is multiply by 3. I'm going to divide by 3. So I do the inverse operation. Then prior to that, they squared, so I'm going to take the square root. Prior to that, they subtracted 7, so I'm going to add 7. And prior to that, they multiplied by 8, so I'm going to divide by 8. That's my roadmap. So let's go ahead and divide both sides by 3 first. And how nice is it that 3 over 3 is just 1? So by design, that works out that way. So you get that quantity 8x minus 7 being squared is equal to 8. The next thing I need to do is take the square root of both sides. If I do that, I'll get 8x minus 7 is equal to the square root of 8. But remember, you have no idea if 8x minus 7 is positive or negative. So I have to list out the fact that it could have been positive or it could have been negative. So there's 2 possibilities there. So right when you take the square root, you have to do that. You can't wait till the end. You have to do it now. Now I'm going to go ahead and add 7 to both sides. I know some people are probably asking me why I'm not simplifying that radical. The reason why is because I haven't talked about radicals in lectures yet, so I don't force anybody to simplify yet. But I will do it at the end for those who know how to simplify radicals. So I add 7 to both sides. So the left-hand side is now 8x. The right-hand side, I could write it as plus or minus the square root of 8 and then plus 7. Or I could have written it as a positive 7 plus or minus root 8. And most of us don't even write the positive in front of the 7. We just write it as 7 plus or minus root 8. And really, that last form is a better form to use. It's not that it's more correct. It really isn't. They're the same number in the end. But this first form, you run the risk of confusing somebody. Somebody might I've seen a lot of students that love to carry that radical symbol too far. And so I have no idea if they're taking the square root of 8 plus 7 or if they're taking the square root of 8 and then adding 7 to it. So by listing the 7 first, you avoid that technical difficulty. So I'm just going to go ahead and do that. That's 8x is equal to 7 plus or minus the square root of 8. Finally, I'm going to divide both sides by 8. Divide this side by 8 and divide the right hand side by 8. And remember, 8 over 8 is just 1. So we get a single x is equal to 7 plus or minus the square root of 8 all over 8. For anybody who's seen the quadratic formula, which I'm not talking about really here, you already can tell that this is an answer that the quadratic formula would generally return. If you don't know the quadratic formula, not a big deal. It's something coming up. But there are a couple things that I need to mention here. One, that you can actually reduce that radical. The square root of 8 is the same thing as saying the square root of 4 times 2. Right? 4 times 2 is 8. And the square root of 4 is just 2. So I could break that up to be 7 plus or minus the square root of 4 times the square root of 2 all over 8. And the square root of 4 is just going to be 2. So it's 7 plus or minus 2 square root of 2 all over 8. That's one little note I have to mention. It's not necessary if you haven't learned radicals yet to reduce this radical, but if you have learned radicals, it's important that you do something like that. The second thing I should probably mention is that, and maybe I'll use a clean sheet of paper for this just to show it, that if you have something like 3 plus 4 divided by 4, that can be broken up into 3 over 4 plus 4 over 4. See how these have a common denominator? If you have common denominators, you can add fractions, right? So that would be 3 plus 4 over 4. So it does make sense that if I have the quantity of 3 plus 4 being divided by 4, I could break it into two fractions with that denominator. That being said, this right here can be broken up into two fractions as well, if so desired. It depends. Some people are sticklers for this. So if it's not really any better than this form right here, but if you have an instructor that requires it, or if you're just curious about it, this can be broken up into 7/8 plus or minus 2 root 2 over 8. And actually this last fraction would then have to be reduced because 2 goes into 8 4 times. So that'd be 7/8 plus or minus root 2 over 4. You see, every step of the way, we got to this final answer over here, and I was actually pretty fine with that. But at the end of a process, you should always ask yourself, can I simplify that? And at the least, this simplification is generally what people prefer. However, you can actually go even further than that by splitting into subfractions. Not required, but it's possible. Now, really, the strength of quadratics comes into play when you're dealing with applications. And this is an application, most applications actually involving quadratics are about parabolic motion, or in other words, like ballistics, throwing a ball in the air, that curve that it makes as it goes up and then down. That's modeled using a quadratic equation. So let's suppose that you drop a ball from a height of 36 feet, and somebody is nice enough to give you the equation for the height of the ball after so many seconds. That equation is h equals 36 minus 16t squared. So that it just depends on what t is. You can find out the height. The part A is just asking, what is the height after a half a second? Well, ask yourself when you see something like that, what they're looking for and what you have. They're looking for the height, h, and what you have is t is equal to 1/2. They told you time is 1/2 a second. So let's plug that in. H is equal to 36 minus 16 times 1/2 squared. Follow the order of operations, so always exponents first. So that's 36 minus 16 times 1/4. And then after exponents, multiplication, well, 16 times a fourth is a 4. And then finally the subtraction. So that's 32. So the height after half a second is 32 feet. Always write in the units at the end as an interpretation. It's kind of important. Part B is asking how long would it take before the ball will hit the ground. And because it's an application, often in applications, you just want to round your answer to so many decimal places. It's silly to say, oh, to somebody, it'll take you 35 halves seconds or something like that. That's a silly answer. So you want to be realistic and answer in decimal places. So let's see what they give you in this problem, in this question, and what they're looking for. They're looking for how long it'll take. So they're looking for t. T equals we don't know. And they're giving you that the height of the ball will be, well, 0 actually. It'll be at 0 feet when it hits the ground. So they're letting you know h is 0 and we don't know t. So back to our equation. H is 0 and we don't know t, so t is just going to remain. And now I can start solving this equation, and you can either list out what's happening to t, right? If you do that, if you list it out, you can say, oh, it's t's being squared, and then it's being multiplied by a negative 16, and then it's being added to, actually, by a 36, right? That's a positive 36 there. So to undo all that, to solve for t here, we'll first subtract from we'll subtract 36 from both sides, and then we'll undo their multiplication by negative 16 by dividing by a negative 16. And finally, we'll take the square root of both sides. So here we go. Subtracting 36 from both sides, I'll get the following. A negative 36 is equal to a negative 16 t squared. And then I'll divide both sides by a negative 16. On the right-hand side, the negative 16s cancel out nicely. So you get a nice t squared. On the left-hand side, negative over negative is positive, and 16 and 36 both share a common factor of, let's see, 4. So 4 goes into 16 4 times, 4 goes into 36 9 times. And then you would take the square root of both sides. So t is equal to the square root of 9 fourths. And remember, you don't know if t was positive or negative, but we'll talk about that in a moment. Since I'm being asked to actually give an approximation to this answer, I'm going to grab a calculator. I don't need to actually reduce this. I can just grab a calculator at this point, even though this is easily reducible. And I'll ask myself, what's the square root of 9 over 4? And that's 1.5 is what it turns out to be. So let me go ahead and do this. So this is going to exactly equal plus or minus 1.5. Now let's talk about that minus part. There's no t represents the amount of time that's passed. There's no such thing as a negative 1.5 seconds passing. So you can throw out in real situations, often you can throw out the negative answer. So in reality, we're interested in t being 1.5 seconds, not a negative 1.5. By the way, just to let you know, you could have done all this without a calculator because the square root of 9 is 3, the square root of 4 is 2. So that is 3 halves or 1.5 as well. In this problem, we're just going to solve a formula for a variable. First thing I see is that I have fractions in this problem, so I'm immediately, not even worried about the problem itself, I'm going to get rid of fractions. I'm going to multiply both sides by r to get rid of the fractions. So r over r cancels nicely, and the left-hand side becomes fr, the right-hand side is still mv squared. The question is asking me to solve for v, so I'll list out what's happening to v. It's being squared, and then after it gets squared, it gets multiplied by m. So I'm going to undo those two steps by dividing by m and then by taking the square root. So let's divide both sides by m first. On the right-hand side, the m over m becomes 1. On the left-hand side, nothing much can simplify there. It's just fr over m. Finally, I'll take the square root of both sides. So v is equal to the square root of fr over m. And of course, we don't know if v was positive or negative, so you're going to have to say it could have been positive, it could have been negative. Solving formulas for variables is usually a skill that students are weak at, and my method of writing down what's happening to your variable is super powerful for solving formulas for variables. So now let's go ahead and get into more applications. If a 30-meter pine tree casts a shadow of, well, 30 meters, how far is the tip from the shadow of the top? How far is the tip of the shadow from the top of the tree? Okay, you always want to draw a picture if you can. So I'll draw a picture here. I have a pine tree, not the best artist in the world. It's 30 meters tall. It's casting a shadow of 30 meters, so let's just pretend that this entire length is a shadow. And I want to know, I'll draw this in light green, how far is it from the tip of the shadow to the top of the tree? I'll call that x. So important to draw a picture, kind of read the problem, understand the problem, label a variable, let x equal distance from top of tree to tip of shadow. Now all we have to do is develop an equation relating all this information with this variable. And of course this is the very famous Pythagorean theorem, because this is a right angle. Pythagorean theorem just says that the leg squared plus the other leg squared should equal the square of the hypotenuse. And if you do that math, that's going to be 900 plus 900 is equal to x squared, or in other words, 1800 is equal to x squared. Take the square root of both sides, you'll get that x is equal to plus or minus, remember, the square root of 1800. And of course, the square root of 1800, or actually x, is supposed to be a distance, so you can throw out the negative. So x itself should be the square root of 1800. Two possibilities for answers here, actually three. One, if you have an instructor that requires you to reduce radicals, which most instructors will, you could say this is like 900 times 2, and the square root of 900 is 30. Or you might have an instructor who says, listen, approximate this length to the nearest tenth of a foot, or meter, actually. So if you do that, you slide on over a handy dandy calculator here, and I'll say 30 times the square root of 2. 42.4 meters, roughly. It's rounded to the nearest tenth. As a final example, we're going to go ahead and find the size of a rectangle that'll fit inside a circle of radius 30 feet. If the length of the rectangle must be 3 times the width. In this case, we're going to draw a picture that has a circle and it has a rectangle inside of it, just like what they're asking us. We know the radius of the circle is 30 feet, so starting from the center of the circle going out to an edge, and notice I'm creating that length to go from the center to the edge of the circle, and also where it intersects the rectangle. That's supposed to be 30. And then I label some unknowns because it's asking what are the dimensions, so I need to know what the length of the rectangle is and what the width of the rectangle is. Now I need to create some formulas. First thing that kind of pops into mind is just using the language of the problem itself. It says that the length of the rectangle must be 3 times the width. So length is equal to 3 times the width. Well, that's our first equation, but we need a second equation because we have two unknowns. And the second equation may not be super obvious, but let's see if we can link up L and W via a well-known theorem. If I continue that diagonal across to the other side here where it's supposed to, I don't have it drawn in perfectly, but that rectangle is supposed to intersect the circle also at this edge right here. If the radius is 30, then this total length that I've shaded in should be 60. So you should have, if you look at that as a triangle, that should be 60, that should be L, that should be W, and this should be a right angle. And now I see I have a second equation because the Pythagorean theorem gives me that 60 squared should equal L squared plus W squared. And instead of writing L when I rewrite that second equation, I'm going to use the fact that L is equal to 3W. So I'm going to take 3W, and wherever I see an L, I'm going to replace it with 3W. I get 3600 is equal to 9W squared. That's just me replacing L with 3W, plus another W squared. Or in other words, 3600 is equal to 10W squared. Dividing both sides by 10, I get W squared is equal to 360. Or in other words, W is equal to plus or minus the square root of 360. Now remember, it's a physical application, so the negative doesn't matter. We can throw that out. So just W is equal to the positive square root of 360. That actually can be reduced if you know a little bit about radicals. That's 36 times 10. Square root of 36 is 6. But square root of 10 can't do anything with that. So I know the width is 6 root 10. Now remember, the length is just 3 times that. So 3 times that is just 18 root 10. And that would be the size of a rectangle that would fit inside a circle of radius 30 feet. Of course, you could always find out what the approximate values for W and L are by using a calculator.